We move on to the last talk of this session, which is by our Rajesh from IMSC Chennai. And he is going to talk about a flat histogram cluster algorithm for hardcore lattice cases. Rajesh, can you share?
Yes.
Yes, okay. Yeah. Please start.
Let me start by wishing Mustan sir and Deepak many more productive years. For many of us doing PhD at TIFR at that time had the privilege of working with both of them, and it has benefited at least benefited us quite massively. Now, I was also fortunate to start working with Deepak again, collaborate with Deepak again in the last 10 years. And I hope it continues for much longer. So, so today I will speak about an algorithm that we were working on. So this is work done with Aswil and Jatin, who are postdocs at Math Science, and Sumedha at NICER, and Deepanchan from Warwick. So even though Deepak is not part of this work, the stimulus is from one of Deepak's work. And since he mentioned, I will use his talk as a motivation for my talk. So in this paper by Anand Mohan Ghosh and Deepak, they had studied the problem of hard rods on a lattice. And this is a figure from their paper. What is plotted here is the mean density difference between the number of vertical rods and the horizontal rods. So that's a nematic order parameter, and that is plotted against the density of rods. And one of the key findings of that paper was that as you increase density, if the rod length is large enough, you have a nematic phase. Nematic order parameter becomes non-zero. But what also can be seen is that the simulations stop at density 0.86. This is because it becomes very difficult to equilibrate the system at high densities using evaporation and deposition moves of one rod at a time. So this problem of equilibration is not restricted to rods alone. It is restricted to any system of particles when the excluded volume becomes large or the density becomes close to full packing. But then a lot of the interesting physics is near densities close to full packing, which is when you have a second transition and so on. So this particular paper therefore made us look for algorithms that are able to equilibrate the system, such systems at high densities. And one possibility is a grand canonical cluster algorithm, which is able to do so. But then we were quite keen to find a flat histogram cluster algorithm that works for such models. So that will be the topic of this talk. So in statistical mechanics, it is the Monte Carlo simulations are very important because exact solutions are few. And the aim is to generate configurations C1, C2, C3, and so on, according to the equilibrium weights. Once you generate such a sequence, then finding the value of any observable is quite easy. And the key, to generate configurations with the equilibrium weights, one has to just choose a dynamics that obeys detail balance, which says that the probability current from C1 to C2 is the same as the one backwards. A convenient rule for implementing detail balance is the Metropolis rule, which says make any dynamical move that changes the configuration. If the change in energy is delta E, you have an acceptance probability for that. The important thing to note is that each simulation is done at a fixed value of temperature or any other parameters. So it would have been much easier if one could determine the density of states directly. If I know the G of E, then the partition function is known for any temperature, and the data for all temperature can be generated in one go. But the question is, how can we generate or determine the density of states in a Monte Carlo simulation. So such Monte Carlo methods are called flat histogram methods in general. So the idea is you say, I don't want the weight of a configuration to be e to the power minus beta e as is normally done. Rather, I will assume some weight of e. So if I have a configuration with energy E, I'll assign it some weight WT. Then I run a simulation using the Metropolis rule with the acceptance rates being fixed by the ratio of the weights. As you run the simulation, then it reaches equilibrium with this weight. You measure the histogram H of E, which is the number of times a state with energy E is visited. Then it's clear that the histogram will be proportional to the density of states into the weight of each configuration. So if I had chosen my weight to be 1 by density of states, then the histogram would have been flat because of this cancellation. Of course, one does not know G of E, but one can use the fact that if I had chosen the correct weight, then the histogram would be flat. Okay. So what is the direct implementation? So you make a guess for the density of states. I call it G1. Then the weight of a configuration with energy E is 1 by G1 of E. You run a Monte Carlo simulation. You measure the histogram H of E. Then H of E is proportional to the actual density of states into weight of E, which I've chosen to be 1 by G of E. So this gives me an estimate of what is my density of states. Okay, I'll call it G2. So at this point, theoretically, you have got the correct G actual. But in practice, this first estimate is a poor estimate, and you can iterate many times to get the correct density of states. However, this sort of approach has many difficulties. Convergence is very slow, and it depends crucially on the initial guess G1 of E. So a more popular version of this one is the Wang Landau algorithm, in which during the simulation, the density of states continuously evolves. So it has a defect that it does not obey detail balance during the simulation, but convergence is extremely fast, and this is a very popular and efficient algorithm. I will not give the details of that particular algorithm. So what I would like to ask is, I will argue later that the Wang Landau algorithm works for any system. But if I use hardcore lattice gases with local moves and Wang Landau, they do not equilibrate. That is my point I'll make later. But let me first tell what we are doing, and then I'll compare with standard algorithms. So I will, so let me define two hardcore lattice gases. One is, I have a lattice, I have a particle denoted by the red side. The nearest neighbor model is, I call 1NN, is when the 4 neighbors are excluded from occupation by any other particle. 2NN is when the next nearest neighbors are also excluded from occupation by any other particle. This is the hard square model, and 1NN and 2NN. I could, of course, define 3NN, 4NN, or different shape particles too. So the algorithm that we are proposing is that you have a particular configuration of particles by this blue line, denoted by these blue particles. You pick a row at random, that is the third row. You first identify what sites in this row are disallowed from occupation due to particles in the neighboring rows. For example, in this case, this red one is, if you can see my cursor, is disallowed from occupation due to the blue particle on the top. So these red circles divide the line into segments. Then you pick a segment at random and evaporate all the particles in that segment. Then you ask, how many ways can I refill this segment, keeping into account that my density of states is G of E. That reduces to a combinatorial problem. So sometimes it is solvable, sometimes you have to solve it numerically in the computer while the program is running. But either way, you enumerate all possible configurations, you assign them a certain weight, and choose proportionately from that configuration. That is the idea. Okay. So that is the rough algorithm. It has two features. One feature is that all the moves are cluster moves, in the sense you evaporate multiple particles at a time and deposit multiple particles at one time. The other feature is that it's rejection free and is biased towards low entropy states. Now, I'll try to argue that both of these features above features are essential.
Rajesh, you have 2 more minutes. Two more minutes.
So I don't have too much time. So what we did for comparison, you have to believe me, is that we defined 2 more algorithms. One of them is unbiased. One of them has no cluster moves, which is but a single side. And then we show that both of them fail. So this is just to show that if I compare with 3 algorithms, only this particular algorithm, what we call strict cluster Wang Landau algorithm, is able to do the job we aimed for. So for example, if I look at the entropy at full packing, which is difficult to access in Monte Carlo simulation, this algorithm is able to do it quite easily. So then to show its usefulness, we obtained the critical behavior for many models in 2 dimension, in 3 dimension, and these covers continuous first order, multiple transitions, columnar order, etc., etc. Okay, and details can be found in these 2 papers. So to summarize, so what we propose is a rejection-free cluster-based flat histogram algorithm. It is able to access low entropy states easily. Currently, we are working on how to generalize it to multidimensional histograms, for example, binary gas, attractive gas, and generalize to spin systems, for example, Ising model, but you update an entire row of spins at a particular time. If one does like this, does it improve convergence and accuracy? And that is my 12 minutes up.
Let's thank Rajesh for a great talk. And there's a question from Sanjeev.
Yeah. Hi. Yeah. Hi, guys. Can you hear me?
Yeah, I can hear. Yeah.
See, you said that this, in some cases, this algorithm doesn't equilibrate, right? That's yeah. So then, what does it mean that with that rate, basically, it doesn't satisfy detailed balance, or you need more time to equilibrate?
Yeah. So I said that if I remove one of the condition, either cluster moves or biasness, when you run those when you run with those algorithms, so there's some criteria by which you realize that the correct G of E is reached. So the histogram should be flat. So it is not able to make the histogram flat within certain time. So if I fix within certain Monte Carlo steps, it should find the correct density of states. It cannot do. If I of course make it infinite time, it will do.
Okay. So it's basically the problem of taking very long time, is it? It's not the problem with the theory of the algorithm, but taking long. No, okay.
It is not a theory. It is just that those particular moves will not is not practical.
Okay.
Typically, how many Monte Carlo moves do you need for the cluster algorithm to get the flatness?
So for example, the hard square 2NN model. So if you do 200 cross 200, in the overall, the full final converged GOP, we get in 10 to the power 7 Monte Carlo steps.
And how does this scale with the size of the system?
Actually, that part we have not done with the system size. We have not. I cannot say.
I see, because any quoting of dynamical critical exponent for the algorithm would be unfair unless you factor that in your definition.
Yes. So I agree. So we have some convergence time, but we have not looked at that with n. Our aim was at that point not that.
Okay. Yeah. Thanks.
Tridib?
Yeah, I have a question, something similar on the line of Sanjeev. So can the flat histogram method be used to simulate non-equilibrium stationary state probabilities without the Boltzmann-Gibbs kind of measure. So you would just simulate the same kind of detailed balance kind of algorithm, but you say that you just need any arbitrary probability measure for the, so, and it will converge to that arbitrary probability measure, right?
See, the final probability measure, you're not dynamics.
No, not that. Of course, the dynamics will not be the perfect to represent.
But then, okay, I'm not. See the whole. Okay, the whole point is that the whole model is described in the role of dynamic. Okay, I will not answer that question. Actually, my up to now my thought was this is only working with equilibrium problems. But since you asked about the final steady state measure, I have not thought it.
Okay. Thanks.
Yeah.
Okay. If there are no other questions, let's thank Rajesh once more. And let's also thank all the speakers of this morning.